All right, welcome once again to another class. I'm still looking at the chemistry gem syllabus, and just like we've been doing, we've been taking the topics one after the other. And today we are going to be looking at a new topic, today, and we're going to be looking at this topic, non-metals and their compounds. Non-metals and their compounds. That's what we are going to be looking at today, and our learning objective. By the end of this lesson, you should be able to, one, predict reagents for preparation of non-metallic gases, identify and compare the properties of non-metals and their compounds, specify uses of non-metallic gases and compounds, determine tests for gases and their ions, and also understand classification and reactions of oxides, and explain the significance of ozone and nitrogen cycle. So let's go into the introduction as we look at this topic, non-metals now. Non-metals are elements that lack metallic properties. They lack metal, and hence we call them non-metals, They lack metallic properties, so we call them non-metals. And some of their characteristics include, one, they are poor conductors of heat and electricity. It's just like the inverse or the reverse of what you have with metals. So they are poor conductors of heat and electricity. They're brittle when they're solid. They're brittle, so they are very soft, can easily be broken. They have low melting and boiling point. Generally they have low melting and boiling point. Maybe with some few exceptions. Anyway, also they tend to gain electrons in reaction. So they tend to gain electrons in reactions to form what we call anions. So they gain electrons to form anions. Okay. Also, okay. So those are the characteristics. Examples of non-metals include oxygen, nitrogen, sulfur, chlorine, and so on and so forth. If you look at the periodic table, the non-metals are the ones that are colored yellow. Hydrogen is typical is called a non-metal instead of it, although it appears to be a part of the group one element, but it is most time categorized as a non-metals. And I want you to ask yourself or go and do a research and look at it. Why is hydrogen, though it appears on the group one or in the group one elements in the periodic table, why is it still classified or categorized as a non-metal? So I want you to look into that and let me know when you get the answer to that. Okay. So hydrogen, carbon, nitrogen, oxygen, selenium, sulfur, chlorine, bromine, krypton, and so on and so forth. These are all non-metals. So they are all non-metals. Okay. So we'll move on now. Let's talk about hydrogen, specifically preparation of hydrogen. In the laboratory, we can prepare hydrogen by reacting zinc with dilute acid. So when zinc is reacted with a dilute acid, it will give us hydrogen. Hydrogen can be produced in that manner in the laboratory. Industrially, hydrogen can be produced from water gas. When you have carbon dioxide and water, reactants give us CO2 and H2. Okay, so industrially we can produce it from water gas. Okay. It can also be made by cracking hydrocarbons from petroleum. So when you crack hydrocarbon from petroleum, you have a smaller hydrocarbon that is formed. The nitrogen is also part of what is given off also. So that's another way we can produce hydrogen in the laboratory now, industrially, pardon me. So we are looking at the laboratory preparation and the industrial preparation. Now, how do we test for hydrogen? Hydrogen basically burns with a pop sound when ignited. So when you want to know if a substance contains hydrogen, All you need to do is just to ignite and watch out for a pop sound. When you get a pop sound, you know, oh, hydrogen is definitely, evolved or present in that particular um, setup, so to speak. Okay, so we can have it this way. We can have the preparation of hydrogen gas using is zinc and dilute acid, dilute HCl to be precise, and we have hydrogen being produced in that manner. Okay, so let's take note of that. Very, very important. The next thing is properties and uses of hydrogen. Now let's look at the properties first. I would say one of the properties is that it is the lightest gas that we have, on Earth. So it's the lightest gas. It is colorless and odorless. Hydrogen is colorless and it is odorless. It is highly flammable. Hydrogen is highly flammable, so it can easily catch fire, so to speak. So we must be careful around hydrogen, whether we are working with it or is in a lab that we are working in. It is highly flammable. Some of the uses of hydrogen are, sorry, hydrogen, hydrogenation of oil. So hydrogen can be used in the hydrogenation of oil. So it's hydrogenation of head and then makes the oil to become hardened, so to speak. So hydrogenation of oil is one use of hydrogen. Also as a rocket fuel, hydrogen is a very important component in rocket. It's used as a fuel, to propel rockets. Also, it is used as a reducing agent in metallurgy. Hydrogen is used as a reducing agent in metallurgy. And for the manufacture of ammonia, which is the Haber process. So when we want to manufacture ammonia, you need hydrogen. So hydrogen is used in the manufacture of ammonia, which is the Haber process. Okay. All right. So we move now and talk about chlorine. Having settled hydrogen with the preparation, the properties and the uses and all that. So we can now move on to another non-metals. And this time around, we want to look at a very, very important non-metal. And this particular non-metal is called chlorine. Chlorine. Let's look at the preparation first. In the laboratory, chlorine is prepared by the reaction of concentrated HCl with MnO2. So when you react MnO2 with concentrated HCl, you have chlorine being produced in the laboratory. Okay. Industrially, chlorine can be produced through what we call the electrolysis of brine. The electrolysis of brine, which is concentrated NaCl. So when you electrolyte, you make brine to go through electrolysis. Industrially, we can produce chlorine. So chlorine is greenish yellow gas with a choking smell. So unlike hydrogen, it is not colorless, but it has a color which is greenish yellow and it has a choking smell. Okay, so this is just like a setup for the production of fluorine, like we can see, the manganese oxide reacting with concentrated HCl. And then we see our chlorine gas being produced in the process. Okay, all right, so that's how to produce that. So properties and uses of chlorine now. I mean, talking about the properties, one, chlorine is poisonous and it is a corrosive gas. The poisonous and corrosive gas. So we must be careful around chlorine. Be careful with your exposure to chlorine because it is poisonous and it is corrosive. Okay. It is heavier than air. Chlorine is heavier than air. Okay, that's another property. Another one is that it reacts with water to form acids. Yeah, chlorine reacts with water to form acids. And uses. Chlorine is a very, very wonderful component of water sterilization. It helps to kill germs and bacteria and water and all that like that. So it's very, very good for water sterilization. Very useful in the urban water treatment or municipal water treatment, as the case may be. So yeah, it's very useful in water sterilization. It's also very good in bleaching of fabrics and paper. Yeah, you have a stain on your fabric, you want to take it out, you can you make use of fluorine, which is an important and major component of most of the bleaching agent that you have around any material that you want to use to bleach either your clothes or whatsoever. Chlorine is a major component, so it is used in bleaching fabrics and also for paper too. Okay, it is also used in the manufacture of HCl, which is a very, very important acid. Okay, it is also used in the production of polyvinyl chloride plastics, that's PVC plastics, and these plastics are very, very useful for plumbing work, for house for building, in building of homes, some interior in some homes, you actually use PVC plastics to, do the inner part of the roof, so instead of you using um the number of asbestos or whatever, you can actually use the PVC plastic, and then it's very, very important. So fluorine is used in the production of PVC plastics, and that's that for that. Okay, so we move along now and we look at oxygen, and we talk about the preparation of oxygen now. Oxygen basically in the laboratory is prepared by the decomposition of hydrogen peroxide. It is prepared by the decomposition of hydrogen peroxide, just like what you can see. Hydrogen peroxide decomposes, and then you have oxygen being produced. So that's how we produce oxygen in the laboratory. That's how we produce oxygen in the laboratory. Okay. So we have talked about the laboratory preparation. Okay, yes, I must include this that for us to produce, we need manganese oxide as a catalyst to help, in this reaction. So that's the laboratory preparation. Industrially, we produce oxygen through the process called fractional distillation of liquid air. When you do fractional distillation of liquid air, you can get oxygen out. So oxygen is very, very important for combustion and respiration. In fact, it's one of the most essential gas you can talk about on Earth. It aids combustion, which is for so many, we use for so many reasons. Combustions in engines, it helps in combustion when it comes to even industrial works and all that, and also for household needs too. We want to make we want to cook our food. We need oxygen to mix up with the gas that would help to cook the foods that we want to eat. Respiration, we can't talk, so we can overemphasize the importance of oxygen in respiration. Without oxygen, most of our body parts or body organs will not function, especially the brain that needs so much oxygen for it to function. So oxygen is necessary for combustion. It's also necessary for respiration. Don't forget that industrially, oxygen is produced by the fractional distillation of liquid air. So you fill air into, a fractionated column, and then it comes out at a particular temperature, and then you can get your oxygen out from that particular system. So laboratory preparation, like we said, this is just like a setup. You have the hydrogen peroxide, then you mix it with manganese oxide, and then it catalyzes that and gives us oxygen. Okay. All right. So classification of oxides now. Oxide can be classified into this. We can have what we call acidic oxide. We can have what we call basic oxides, amphoteric oxides, and even neutral neutral oxide. For acidic oxides, examples include CO2 and SO2, carbon dioxide and sulfur dioxide, and basically they react with bases. And for basic oxide, you have oxide like oxides of sodium and oxides of calcium, and these also react with acid. Then we have amphoteric oxide like oxides of aluminum and then oxides of zinc. They react with acid and base, because they're amphoteric, so they're in between like that. Then we have neutral oxides like carbon oxide and N2O, which are neither acidic nor basic. Basically, for acidic oxide, you can test them by the ability to turn blue litmus paper to red. Okay. All right. So that's that concerning classification. The next thing that we need to look at is ozone, which is O3, ozone. Okay. Ozone is an allotrope of oxygen formed by UV radiation in the upper atmosphere. So ozone is formed by the ultraviolet radiation in the upper atmosphere, and we said it's an allotrope of oxygen. The importance of ozone includes it helps to absorb harmful UV radiation. The reason why it seems as if we are shielded from this radiation is because of ozone that helps in absorbing, and that's why we can't shout this enough by saying that we must be mindful of our anthropogenic activities that can affect, the ozone layer. Because when the ozone layer is damaged, it has so many, debilitating effects on us as human beings. So it helps to absorb harmful UV radiation from getting onto the earth. And when it does that, it keeps cancer away, especially skin cancer. So it is important because of that. Another thing is that it protects living organisms. Yes, it has as a shield for us living organisms. Yeah, it protects us from this UV radiation that can result in carcinoma or cancer, as the case may be. Um, we must also be able to state, and I've said this before, but I can't say it enough, and I cannot overemphasize it by saying that excessive chlorofluorocarbons, as CFC, destroy ozone layer, which leads to ozone depletion. So we must be mindful of, the use of CFC in certain component that we make use in our everyday life. And so many legislation has gone towards, curbing the use of CFCs, so that to stop or to guide against the depletion of ozone layer, which can be very, very dangerous, very, very debilitating to us as humans. So CFCs can be found as in refrigerators. They can be found in some of our aerosols or our sprays, so and those perfumes and other things that we use and all that. So we must be mindful of the substance that we make use of and the composition so that we don't impact upon the ozone layer negatively. That will now have a general bad what's it called effect on us as humans or even animals too. Okay, so this is the sun, and then you have the UV, you have ozone being formed like that. So that is how the setup for the formation of ozone. Okay, so that's that for that. Okay, so we move on now and we talk about sulfur, its properties, and then its halotrope. Sulfur is also another non-metal, and the halotropes of sulfur include rhombic sulfur, monoclinic sulfur. These are some of the allotropes of sulfur. And the properties of sulfur includes that they are yellow and brittle solid. They are yellow, they are brittle, and they exist in the solid state. Okay. Another thing is that they are insoluble in water. They are soluble in carbon disulfide, but they are not soluble in water. So there's no amount of water that you can put to dissolve them. They're insoluble in water, but they are very soluble in carbon disulfide. Okay. They are used in organization of rubber. Yes, very important. Sulfur is used in organization of rubber, and we look at some of these oxides of sulfur dioxide, and sulfuric acid. Basically, sulfur 4 oxide SO2 is prepared by burning sulfur in air. When sulfur is burnt in air, you can get sulfur 4 oxide. What are the uses of sulfur 4 oxide? One use is that it is used as a bleaching agent. It can be used as a bleaching agent. It can be used as preservative in wine industry. So it is used as a preservative in wine industry. Then the next thing that we need to look at is the preparation of H2S sulfuric acid using the contact process. Now, what happens is that there's a catalytic oxidation of SO2. So we have sulfur reacting with oxygen to give us SO2. Then SO2, is catalytically oxidized, to produce SO3. And then when that happens, there's an absorption of SO3 in H2SO4 to form oleum. So SO3 is absorbed in H2SO4 and it forms oleum. I think okay, yes, that should be H2S2O7 oleum. Okay. So the laboratory setup looks like this, okay. That's just the laboratory setup for you, for the preparation of sulfur 4 oxide. Okay. So this is the laboratory preparation, so to speak. So for hydrogen sulfide, we have its properties include it is colorless, it smells like rotten egg, very terrible smell. It is a weak acid and it's also a reducing agent. What are the tests for hydrogen sulfide? The black precipitate, they form black precipitate with lead-2 ion. So when you bring hydrogen sulfide close to lead-2 ions, they form black precipitate and they turn lead acetate paper to black. They turn lead acetate paper to black. But we must be cautious and be very, very mindful that H2S is highly toxic, is a very highly toxic gas. So we must be mindful of that. Okay. The next one is nitrogen and the preparation now. The laboratory preparation of nitrogen. In the laboratory, nitrogen is prepared by the decomposition of ammonium nitrite. Ammonium nitrite. So when ammonium nitrite decomposes, it will give us nitrogen, and also water will be also be produced. Okay. So industrially, nitrogen is also produced using fractional distillation of liquid air. So we must also be mindful that it is produced by fractional distillation of liquid air. That's for nitrogen. So nitrogen is inert under ordinary conditions. Yeah, it is not reactive under ordinary condition. So this is like the setup for the production of nitrogen in the laboratory, just like what we can see there. Okay. On to the next one is ammonia, preparation and properties of ammonia. Laboratory preparation, it is produced by heating ammonium salt with alkaline, e.g. sodium hydroxide. So when you eat, pardon me, please, when you eat ammonium salt with alkaline, you have ammonia being produced. Industrially, it is produced using what we call the Haber process, and it involves the reaction between nitrogen and hydrogen to give us ammonia. So that's the Haber process. Okay. Ion catalyst at high temperature and pressure is included in this Haber process for us to be able to produce ammonia. Okay. What are the properties of ammonia? Number one is that it has a pungent smell. Ammonia has a pungent smell. For some of us that have worked with ammonia before, we know what the smell looks like. It has a pungent smell. Also, it turns red litmus paper to blue, showing that ammonia is an alkaline, is alkaline, so it turns red litmus paper blue. And it's also very useful in fertilizers. It's a major component of fertilizer. It's very, very useful in the production of fertilizer that aids, our crop, and agricultural processes. Okay, so this is like the setup for the preparation of ammonia. So, that is how it looks. So that's how we prepare, ammonia in the laboratory. Okay. So I want to look at triazonitrate 5 acid now, HNO3, triazonitrate 5 acid. And in looking at this, we start off with the preparation. Basically, it is prepared by the oxidation of ammonia to nitrogen 1 oxide, then to what's it called? To nitrogen 4, then to nitrogen 4 oxide. So NO2 absorbs in water. When NO2 is absorbed in water, you can have what HNO3 being produced. So what we have is oxidation of ammonia to NO, and then to NO2. And then this NO2 is then absorbed in water to give us triazonitrate 5, acid. What are the properties? Strong acid is a strong acid, and it's a very, very good oxidizing agent. Okay. What are the uses? It is used for manufacture of explosive, TNT. It is also used as for making fertilizers. So it's very, very good for making fertilizers. Okay. So the setup for the preparation looks like this. So this is how the setup looks like. And then triazonitrate 5 acid is produced thereafter. Okay. What are the tests for non-metallic ions? Some of the tests that we make use of for chlorine. It will give us a white precipitate with AgNO3. So chlorine gives a white precipitate with AgNO3. The white precipitate is actually AgCl that is being formed. So it gives a white precipitate with AgNO3. Also, it gives a white precipitate with barium chloride, the same thing. So sorry, pardon me. That's for chlorine, gives a white precipitate with AgNO3. And I said the precipitate is AgCl that is formed, okay? Then sulfate ion on the other hand is another metallic ion, and this one gives a white precipitate with barium chloride. Pardon me, please. So when you react any substance that contains sulfate ion um, barium chloride, it will give us what we call a white precipitate. CO3, carbonate ion will we notice an effervescent when it is reacted with dilute HCl. Basically, the effervescent is just like CO2 being evolved, being released, so to speak. Then ammonia evolve on heating with sodium hydroxide. Okay. Then for NO3 minus, we have the brown ring test. So these are some of the test result for non-metallic ion. So we can always test this out using what we call qualitative analysis. So using qualitative analysis, we can actually test what ion is present in a particular substance or compound, as the case may be. Okay. Now, let's talk about the importance of nitrogen cycle now. Nitrogen cycle maintains soil fertility. It's very, very important for soil fertility. What are the steps, Number one is through nitrogen fixation, and then we have nitrification, and then denitrification. And basically, nitrogen cycle is very, very essential for life on Earth. So, nitrogen cycle maintains soil fertility, and the steps that involves the nitrogen cycle are nitrogen fixation, nitrification, and then denitrification. Okay. Let's summarize this lesson, what we have learned so far, and by saying that non-metals like hydrogen, oxygen, nitrogen, chlorine, sulfur play vital roles in chemistry. Their compounds, e.g., acids, gases, have key industrial uses. So they have key industrial uses. Then understanding properties, preparation reaction is crucial, and that's why we looked at one after the other, the preparation, their properties, and then their uses, as the case may be. So with that, we have come to the end of this lesson. Please, if you have a question that you'd like me to answer, or you have a portion of the lesson that is not so clear, please put your answer, sorry, put your question in the comment section. Put your questions in the comment section. So let me evaluate the lesson with this question. Which gas is tested with a glowing splint? Which gas? Is it hydrogen? Is it oxygen? Is it chlorine or nitrogen? The second one says, which oxide is neutral? Is it CO2? Is it SO2? Is it CO or Al2O3? So tell me in the comment section which of the oxides you feel is neutral. Yeah. So let me know. What is used to test for chlorine ion? Now we can use AgNO3. We can make use of HCl. We can make use of sodium hydroxide. We can make use of lead nitrate. So which of them is used to test chlorine ion? So you pick one and you let me and let me know what you feel the right answer is in the comment section. What is the industrial method for ammonia production? We've talked about this. So what is the industrial method for ammonia production? Is it the Haber process? Is it the Ostwald process? Is it the contact process or the Downs process? Okay, so please let me know what you think the answer is in the comment section, and then I will react appropriately to it. Okay. Okay, so let me pause at this point and We'll take a breather, just a short breather, and then we'll move into metals and their compound. That's the next topic that we want to look at. Is already on the screen. So metals and their compounds. So is the next thing that we're going to look at. But let's just take a little breather and just take a little pause, and then we'll start this very, very shortly while you try to reflect on the first lesson that we've had on non-metals and their compounds. So we'll look at metals now and their compounds. So I'll go off for some few minutes, and then I will come back on, and then we'll continue from there. Okay. So we continue with metals and their compounds. That's the next one. What is the learning objective for this particular excuse me, please, for this particular lesson? It is it's expected that by the end of this lesson, students should be able to identify the physical and chemical properties of metals, classify metals into different groups such as alkali metals, alkaline earth metals, and transition metals. Explain the extraction process of common metals and their uses. Describe reactions and laboratory tests for metal ions, and then understand the formation types and importance of alloys. So these are the expectation, or this is what I expected that you should be able to learn by the end of this lesson. Okay, so we look at the first in the introduction to metals. Metals are elements that typically exhibit high electrical and thermal conductivity. Luster, that is luster rather, the shining appearance, malleability, ability to be hammered into sheets, and ductility, ability to be drawn into wires. They usually have high melting and boiling point, although exceptions like mercury exist, which is liquid at room temperature. Okay. So in chemical reactions, metal tends to lose electrons, forming positive ions, cations to be precise. This loss of electron is referred to as oxidation. We've talked about this when we're considering redox reaction. Okay. So examples of metals include sodium, calcium, iron, copper, and so on and so forth. On the periodic table, you can see them outlined. You can see the group 1 element, the group 2 element are all metals. And then when you go to the group 13 elements, you have the likes of aluminum, gallium, and all that. These are all metals also. So these are some of the metals that we have, you know. You discovered that their degree of how do I say it now? Their level of okay, let's just scratch that because I don't want to confuse you. So these are metals. You have the alkali metals, the group 1, the alkaline earth metals, group 2. In the middle section, in the mid section, you have the transition metals, and then you have all the metals that are colored orange on the periodic table there. So these are all examples of metals. So we want to start by looking at the metals and looking at the group 1 element or the group 1 metals. We call them the alkali metals. The alkali metals include lithium, sodium, potassium, etc. And they are the most reactive metals on the periodic table. They are soft enough to be cut with a knife and are stored under oil to prevent them from reacting with oxygen or moisture in the air. Okay. Basically, when alkali metal reacts with water, they produce a metal hydroxide and nitrogen gas. And so we have to safeguard, you know, the ability to react with moisture and air because they are very, very reactive. So that's one thing. So this reaction, that is the reaction between alkali metal and water, is highly exothermic and vigorous, especially for potassium and sodium. What are some of the application of alkali metal? Sodium vapor is used as street light, giving a bright yellow glow. And then potassium compounds are important in fertilizers. Okay, so they are important fertilizers. So let's take note of that. So these are the alkali metals, and just a pictorial representation. Okay. And then we have the alkaline earth metals, which are the group 2 elements. Alkaline earth metals like magnesium, calcium, barium are less reactive than alkaline metals, but still react with water and acid to form hydroxide and release hydrogen gas. So examples, we have calcium oxide known as quicklime is produced by heating limestone in and is used in making cement. Magnesium burns with a bright white flame and is used in fireworks. And a typical reaction for alkali earth metal is a reaction between them and water. So these metals are crucial for building materials and biological system, e.g., calcium in bones, very, very important. Okay, and not only that, even if you see magnesium are very, very important component of antacid, which is used for to guide against acid reflux. So they are very, very important in biological system and also in building material. So these are just a diagram, a pictorial representation of some of these the alkaline metals. You can see their appearance, so to speak. Okay. All right, now, so let's move on and talk about transition metals. They are also a kind of metal. So we have the alkaline metal group 1, alkaline earth metal group 2, then we have transition in the middle. So transition metals are found in the central block of the periodic table. That is group 3 to group 12. They have several important properties. And yes, just like you can see them, they are smack in the middle, of the periodic table. So they occupy groups 3 to group 12 on the periodic table. So these are the transition element, the first row transition element, the second row transition element, and so on and so forth, like that. Okay. So that's that for that. One of the properties of transition elements is that they exhibit variable oxidation states. They can exist in multiple oxidation states. Like take, for instance, iron can exist as +2 and as in a +3 oxidation state. Also, they form colored compounds, example, copper 2, is blue. And basically, it's because of their d orbitals, that's one of the reasons why they can actually form, colored compound. They have, partially filled or completely filled d orbitals, as the case may be. And this is also very contributory to the ability to form colored compounds. They often act as catalysts, e.g. iron in Haber process for ammonia production. So they often act as catalysts. Even nickel, hydrogenation of oil, they often act as catalysts, and then they form complex iron. Yeah, they have the ability to form complex ion, and some of the applications include copper ion are essential in electricity conduction and appear blue in solution. Most of these electricity components that we have are even made of copper. You have copper wire in the coil of a ceiling fan. You have the copper, which is very, very important. And so many electrical appliances that we use copper, for as a wire, so to speak. So it's important for electricity and electricity conduction, and also transition metals are crucial in industry for manufacturing catalysts and also for manufacturing other materials. Okay, so what are the methods that we use for extractions of metals? Now, metals are extracted based on their position in the reactivity series. When you look at the most reactive of them, you starting from potassium, sodium, these are very, very reactive. Then the least reactive, then you're looking at copper, lead, tin, and so on and so forth. So if you look at from ammonia, from aluminum upwards, you see that they cannot be extracted using carbon. But when you look at it from zinc downward, it can be extracted using carbon. Okay, so this will also inform the type of electrodes or the choice of electrode that we use in their extraction process. Okay, so highly reactive metals, e.g. sodium, aluminum, are extracted using electrolysis because they cannot be displaced easily. Okay, moderately reactive metals like iron, zinc are extracted by chemical reduction, often using carbon, which is coke, in a blast furnace. And then least reactive or less reactive metals, e.g. gold, occurs naturally and do not require chemical extraction. So let's take note of these important point. Okay, so extraction methods are energy intensive and require careful choice depending on metal reactivity. Okay, so the metal reactivity informs, the extraction method that will be applied or that will be used, for extracting such a metal. Okay. All right, so the blast furnace process now for the extraction of iron. Now, the blast furnace is used to extract iron from its ore, which we call hematite, Fe2O3. And here is how it works. This is basically the setup for the extraction of iron using the blast furnace. This is just how the layout or how it looks like, and each of the processes that it will go through before you can have, iron being extracted. So there's certain key reactions that take place inside the furnace. And the first one is that carbon burns in hot air to form carbon dioxide. And we see that in the blast furnace. And then the next one is that the carbon dioxide reacts with more carbon to produce carbon monoxide. Okay. Then we have the carbon monoxide reduces iron 3 oxide to iron. So it reduces iron 3 oxide, it reduces it to iron. So the molten iron sinks to the bottom of the furnace and it's tapped off, so we have limestone is added to remove impurity, and this forms slag, which is calcium silicate, so to speak. So that is what happens basically in the furnace. So the process is the backbone of steel production globally. Without this process, we cannot have steel. That is very, very important for so many processes, industrial work, industrial processes in the world. Okay. So extraction of copper now. Copper is usually extracted from sulfide oil, like sulfide ores, like chalcopyrites. What are the steps? Roasting. The ore is heated in air to convert it to sulfide, to convert sulfides into oxides, please. Convert oxides into to convert sulfides into oxides, okay? And then reduction, the oxides are reduced using carbon. Then after that, you have a purification whereby the copper is purified by electrolysis. And then we have the anode, which is the copper is purified by electrolysis, where the anode is impure copper, the cathode is pure copper that is deposited. And then the electrolyte is acidified copper 2 sulfate solution. So that is how the setup looks like for the extraction of copper. Yes, of copper. So we have something like that, that helps in the extraction of copper. Okay. So okay. So we move along now, talk about reactions and tests for metal ions. When sodium hydroxide is added to solution containing different metal ions, precipitate are formed, especially when you have calcium 2 plus, it will form white precipitate that is insoluble in excess sodium hydroxide. So this is a qualitative test for determining if calcium ion is present. So it forms a white precipitate with sodium hydroxide, but it is insoluble in excess sodium hydroxide. Then for iron 2 to be precise, a green precipitate is formed with sodium hydroxide. For iron 3, a brown precipitate for copper 2, a blue precipitate, and for aluminium 3, a white precipitate which is soluble in excess sodium hydroxide is formed. So this test is key in qualitative chemical analysis for identifying unknown metals and unknown metal ions. Okay. All right. So that's that for that. So let's look at alloys and their uses now. Alloys are mixtures of metals and sometimes non-metals designed to improve, properties like strength, hardness, and resistance to corrosion. So when you do an alloy, you are mixing a metal, sometimes with the non-metals, and basically what you're trying to do is that you want to improve their properties, like you want to improve their strength, you want to improve their hardness or their resistance to corrosion. So when you have an alloy like steel, and steel is made up of iron and copper, and steel is used in construction, in car bodies, even in the bodies of our planes, and so many, and ships, and so on and so forth, like that. So steel It's an alloy of carbon and iron. Brass is an alloy of copper and zinc. It's used in making musical instruments for locks and so on and so forth. Bronze is an alloy of copper and tin. It's used in making statues and medals. And then solder is an alloy of tin and lead that is used in electrical wiring. It joins, in joining components. So alloys are stronger and more versatile than the pure, metals. So we must take note of that. So these are the various alloys that we have and their components and also their uses. Okay. So we've talked about this. Okay, just like a diagram to just buttress what we are talking about. Bronze is about 78 to about 95% of copper, and then maybe about 5 to 22% of tin. For gold, you can have copper, and then we can have silver, just allowing them, sorry, pardon me, for brass, rather, you can have the copper and zinc, their composition and their percentages are what are listed below in the diagram, okay? So importance of metals and their compounds. Importance of metals and their compounds. Sodium is important. Is used in producing sodium hydroxide. Sodium hydroxide is a very, very important chemical in the laboratory. And this is used in is applied in the making of soap, in the textile industry and so many other industries that sodium hydroxide is deployed. Calcium is an important compound from calcium is calcium carbonate, CaCO3, and it's very important for making cement and also for lime, lime production. So aluminium, we have aluminium oxide, which is used for aircraft body, because they are light and strong, then tin, it is for tin coating. It protects food cans from rusting. So you have those cans of food that we buy, cans of milk and cans of so many other food items that we buy. They are made up of tin. They are coated with tin because it protects food cans from, getting from rusting. So these metals and the applications are very, very germane, and it's something that we see in our everyday life. We can see them deployed in various sectors, various areas of life, and they are quite useful. So we can read up more to get more information about these metals and their applications too. So let me summarize by saying that metals display typical metallic properties, conductivity, malleability, ductility, and they vary in reactivity. Extraction methods depends on their reactivity also. Transition metals are versatile. They form colloid ions and act as catalysts. We also said that alloy combines the best properties of metals, and we state certain alloys and what their big components are. And we also talk about metal compounds and then their wide industrial application, how they are widely used in the industry. So these are some of the things that we touched on in the course of this lesson. So if you have any question based on what you have discussed so please put your question in the comment section and I will react appropriately to it. Okay. Okay, let me quickly evaluate this lesson with the following question. Which metal is used in aircraft production? Is it iron? Is it tin? Is it aluminum or zinc? So let me know what you think the right answer is in the comment section. The second one says, which ion gives a blue precipitate with sodium hydroxide? Is it iron 2, copper 2, calcium 2, or aluminum 3? So let me know what you feel the right answer is in the comment section. Hematite is an ore of which metal? So please, let's see what you think the answer is in the comment section. Looking at the options that we have there, just tell me which one you think is the right one. What is the main use of solder? What is the main use of solder? Is it for roofing, for cooking, electrical work, or for farming? So let me know what you feel the answer is there. So I want to say a big thank you for listening and for participating in the course of the lesson. I will see you again in the next class. Thank you.